Hello class. I decided to break this presentation into parts, and so we're going to do skeletal muscle part 2 and talk more about the whole cell and how fibers build into a muscle. So we're going to talk about the parts of a twitch, how twitches work, different kinds of twitches, isometric and isotonic contractions. Muscle has quite a bit of connective tissue, so we're going to talk about what's called the series elastic component of muscle. We're going to talk about the length tension curve for a muscle fiber versus a whole muscle. Now when we use our muscles and contract it, we usually try to pull a load. So what does that mean? You put a weight on it or you carry something. And the more you load a muscle, the slower it's going to contract. And where we need to go eventually is that muscle contractions are graded. You can have a tiny contraction or a big contraction. And we grade our contractions through two processes. One is called recruitment and one is called tetany. And so we want to think about how those two processes happen. So what you see right here in our upper tracing, you see our resting membrane potential is about minus 90 millivolts. So minus 80, minus 90, muscle fibers are more negative than neurons. At least central nervous system neurons. And you see right here we've had an action potential. Notice there's not a lot of building up, because if we have acetylcholine released at the neuromuscular junction, having an action potential is a sure thing. Essentially, the graded potential at the motor end plate is about 60 millivolts. We're always going to reach threshold. So we're always going to have an action potential in the muscle. And after the muscle has an action potential, then the muscle's going to have a twitch. And in this particular graph, we're measuring tension. So this is actually an isometric contraction. We'll talk about why that is. So there's a little period where nothing happens, then you see tension developing, then you see the muscle relax, and that happens over at least 130 milliseconds. So it's important to realize that the action potential is a very short event compared to a twitch, which is a much longer event. I've alluded to this before, but a single alpha motor neuron and all the muscle fibers it innervates is a motor unit. So here we have an example of one motor unit. And then below we have two motor units. So there's the red motor unit and then there's the orange motor unit. Notice that the fibers are all mixed up. So it's not like you have collections of fibers in one motor unit or the other motor unit. They're all mixed up, and this is a good idea, because your motor units are going to be activated in alternative timing, such that if you have to have an extended contraction, one motor unit can be resting while another motor unit is contracting. And so having them all infiltrated with one another helps maintain tension across the belly of the muscle. It's a really good idea. So what is the deal with isometric versus isotonic? Isometric means basically same length. So here we have a muscle fiber. We're able to stimulate it. But the thing is, we don't allow the muscle to shorten. We have a device called a force transducer. So as this forms lots and lots of cross bridges, it generates lots of tension. And we can see that on this record. So there's a little bit of a latent period. Then there's the contraction phase, the relaxation phase. That's an isometric contraction. So I don't know that I've told you guys this about myself, but I did my PhD looking at single muscle fibers and making them contract. I didn't use an electric stimulator. I used ion baths, different concentrations of ions, in order to make them contract. But that's what I did, and I studied isometric contractions. I didn't want my cells to shorten very much. I wanted them to generate tension. So that's usually your physiologist's favorite contraction. However, we also can study isotonic contractions. Isotonic means same load or the same tone. Isotonic contractions are shortening contractions. So here you have a fiber that can be stimulated, it can shorten, and it can pull a load. So notice the latent period is a lot longer than the latent period up here. And why is that? Well, because initially you have to contract and generate enough tension to lift the load. So that takes some time. So in this latent period is an isometric contraction happening that we can't measure yet. So what happens during the latent period? Well, you have an action potential. You flip the dihydropyridine receptor. You open the ryanodine receptor. You let calcium come out of the sarcoplasmic reticulum. It diffuses into the cytoplasm. It finds troponin. It pulls tropomyosin out of the way. You start getting cross bridges. Your first part of your contraction is isometric, and then it becomes isotonic, and then you can start to see it. So we have much more going on in the latent period. Notice it shortens, and then it lengthens again. It shortens, then it lengthens again. And this is the kind of contraction we can do work with. So the load is going to influence how your muscle can work. So I put a really light load. I can shorten a lot, I can do it very fast, and then I can relax and put the load down. Notice if I lift a heavier load, I may not be able to pull it as far. And if I lift a really heavy load, I may not be able to pull it very much. And I might get a load that's so heavy that I have no isotonic contraction. It's all isometric. And that's kind of what an isometric contraction is. It's like pulling something so heavy you can't lift it. So you're pushing against the wall. You can't move the wall. You've got contraction, but you're not moving anything. Or if you're picking up a load and moving it, then you're doing isotonic. I think about, in terms of efficiency, moving intermediate loads are probably the best. Imagine I go to the grocery store, I come home with all my groceries. If I try to carry them all at once, I'm not going to get very far. If I carry them in an item at a time, I can do each trip pretty fast, but I'm not being very efficient. My best efficiency, maybe I'm carrying 1 or 2 grocery sacks at a time, and that's like that. So I get my best efficiency with an intermediate load. The load is also going to influence how fast you contract. All right? So if I don't have any load, holy buckets, I can really shorten fast. I'm not moving a load though, I'm not really doing anything. As I add a load, the contraction gets slower and slower, and I get to a point where the load is so heavy I can't lift it at all. And I might have a load that's so heavy it actually makes my muscles lengthen. This is called an eccentric contraction. Eccentric contraction would be like a chin down. You're contracting, but you're lengthening the muscle. You chin up, you chin down. Don't ask me to do that because I can't do that, but maybe some of you can relate to that. So it's maintaining tension or contracting while you're actually lengthening the muscle. All right, this is a beautiful diagram. I love talking about this diagram. This is a length tension curve. So in my x-axis, I've got percent muscle length, and then my percent maximum isometric tension. So I'm starting at some length, and then when I start at that length, I contract and I get a certain amount of tension. So there's a sweet spot where I get my best tension. It's a certain length of a sarcomere, and it turns out to be 2.2 microns is the best length of a sarcomere to have a good contraction. And what do you see? You see that actin and myosin have a beautiful amount of overlap, so that when calcium comes along, oh, I'm sorry, that's happening. So that when calcium comes along, you have the best amount of overlap between actin and myosin. Then calcium comes along, you can grab those cross bridges and you can shorten. Now the thing is, if your muscle starts out too short, it's like the muscle's all disorganized. It's like you've taken the muscle and smushed it all up, and the little myosin heads are just going all over the place, and they don't know where to grab, and this little myosin head grabs the wrong actin, and it's actually interfering with the contraction. So you don't get its best tension because you're so short. You've smushed up your contractile apparatus, and it's disordered. You have a lot of disorder that interferes with your ability to contract. And if you smush it up too badly, you're not going to get any tension. On the other side of this curve, you've stretched it too much. You've stretched it so much there's hardly any overlap between actin and myosin. It's really hard for myosin to attach onto actin. It's really hard to get that contraction going, and then your tension drops. So we want to live in the sweet spot of the right amount of overlap so we can get a nice contraction. So this is the length tension curve. It was developed by a guy named Al Gordon. Al Gordon was the PhD advisor of my PhD advisor, Sue Donaldson. So the guy that invented this, or the guy that discovered this, is my scientific grandfather, and I'm so proud of that. I can't stand it. All right. We can relate this to a whole muscle. All right. So as you stretch the muscle, the tension in the muscle goes up, and then you get your peak active tension. But the thing is, as you stretch the muscle more and more, and you disrupt the overlap between actin and myosin, your tension starts to go down, but then it starts to go up again. And what's this tension? Well, this tension is sort of a false tension. It comes from the connective tissue. So you're getting a high amount of tension in the whole structure, but it's not because you're forming cross bridges. It's because you're stretching out your connective tissue. So if you were to remove the effect of the connective tissue, you would see that the tension drops just as it does in the single fiber. So this is a passive tension, and it's masking the fact that your active tension is going down. All right, now, one twitch is not going to do anything. I'm never going to be able to drink my coffee with one little twitch. But we have to remind ourselves, what is the property of an action potential? It happens very quickly, in just a few milliseconds. But a twitch takes 100 milliseconds. So if I stimulate, and before the twitch has the ability to relax completely, and I stimulate it again, I can add a twitch on top of the other one. I stimulate again, I add another twitch. So my whole displacement, or my whole tension, gets bigger and bigger. I can get to a point where I stimulate so much that the fiber doesn't have any chance at all to relax, and I'm adding twitches on top of twitches, and I get something called tetanus. Now what's happening on the cellular level? What's happening is that action potentials are over very fast, but the muscle is still engaged in calcium release. Well, you add another action potential and you get more calcium release. So when you have this big smooth contraction, the calcium release is high and steady, and it exceeds the ability of the SR to pump it back in. So you've got a really high, steady calcium level that allows you to maintain this prolonged contraction. So at the end of the day, it ends up being about calcium. So I can stimulate a whole lot, get a tetanic contraction, but notice what's going on here. I continue to stimulate, but the muscle says, I'm not doing it. I just can't do it anymore. That's a process called fatigue. And quite frankly, we don't really understand fatigue. It's not lactic acid. It's just simply not that simple. And there are a lot of theories. Is potassium building up too much in the T-tubule? is there something going on with phosphate and calcium and that sort of thing? Nobody knows. But here, the muscle rests a little bit, we stimulate it, we give it a tetanic stimulus, and fatigue happens even faster. So there's some chemical event going on that is causing this muscle to fatigue. And maybe in high school or in other courses you've been taught it was lactic acid. It is not. That theory has been disproven. There's something else that's responsible for fatigue. Now, another way to build a contraction is to add motor units. So here we stimulate the muscle and we get a motor unit. Then we increase the stimulus and we get another motor unit, and our tension goes up. And we increase the stimulus even more, and now we get another big motor unit. We haven't talked about types of muscle yet, but you may know we have fast twitch fibers and we have slow twitch fibers. The slow twitch fibers don't fatigue, but they stick around a lot, and they have the lower thresholds, and they're recruited first. Then we recruit the middle-sized ones, then we recruit the big ones. So, your friend is at your house, and you're having a good time watching a movie and having a little popcorn and whatnot, and while you've been watching the movie, there's been a snowstorm. And you go out and your friend's trying to go home and they're stuck in a snow pile. So you got to go out there and you're going to help your friend get out of the snowbank. And you lift with everything you've got. You are using every single unit you have. You cannot immediately jump to your fast twitch. You have to recruit the smaller ones, then the middle-sized one, then the big ones. And you're using everything you've got to lift that car out of the snow. And then they go down the road because you were a big, strong person getting their car out of the snow. So that's the principle of recruitment. Once the fiber reaches, or once the muscle reaches its maximum tension, it can't get any bigger because you've recruited all your muscle fibers. Okay, let's go on, and I'm going to introduce the idea of a stimulator at the neuromuscular junction. We're going to talk about the energy sources for muscle, and we're going to talk about co-activation and use of antagonistic muscle pairs. All right, so the nurse anesthetists use a device in the operating room called a neurostimulator. And essentially what they're doing is assessing the state of the neuromuscular junction. The neuromuscular junction might need to be blocked during a surgery so we can keep the patient still. So a drug is given that blocks the acetylcholine receptor, and it could be a non-depolarizing blocker that binds to the acetylcholine receptor and keeps it shut, or it could be a depolarizing blocker that binds to the receptor and keeps it open. But the anesthetist has to assess that neuromuscular junction. Is it blocked or not? So you can give a twitch stimulus. A twitch stimulus would be a suprathreshold stimulus that's going to evoke one stimulus. So it has to be large enough, and but not a high frequency. So maybe you're stimulating for like part of a millisecond, and you're stimulating once every 10 seconds, something like that. You could do 4 of those in a row. That's called a train of 4. And then there's an assessment to say if I have 3 of 4 of those twitches, or if I have 2 of those twitches, or if my twitches are smaller, I can make a prediction about how much my neuromuscular junctions are blocked, or how much of the block is being is returning after the drug is wearing off. and I would love it if the nurse anesthetist would talk about this in class. We also can give a tetanic stimulus. So what would a tetanic stimulus would be? You'd have to have a high frequency of stimulations. So you have a high rate of action potentials so that you see the fusion of the twitches. So, you know, you're stimulating 50 times a second or something like that to get that smooth contraction. Now, my last notation here, post-tetanic potentiation. So what can be seen in the clinic is that you give a patient a twitch stimulus, then you give a patient a tetanic stimulus, and then you give them another twitch stimulus. And the second twitch is bigger than the first twitch. So a post-tetanic potentiation can happen under the use of some anesthetics or some drugs. It happens physiologically because you have a collection of calcium in the cell, and then when you stimulate the twitch the second time, you've got bigger calcium and you've got a bigger twitch. That's how it happens physiologically. So I look forward to, so I'm just introducing the terms. We'll talk more about it in class and discuss how this whole thing works. All right, so muscle needs ATP. It needs ATP for lots of things. It needs ATP to run the sodium-potassium ATPase so you can have a membrane potential. It needs ATP for the calcium ATPase so you can pump calcium back into the SR when it's time to relax. And it needs ATP for the myosin ATPase, because remember, myosin needs ATP to do the power stroke, and then needs a new ATP to come along so it can let go and that sort of thing. So where are we going to get ATP? One place we can get ATP is from something called substrate level phosphorylation. And that is creatine phosphate with the help of CPK. What that means right now is escaping me. Creatine phosphokinase, and then you take the phosphate and you put it on an ADP and you make an ATP. So that's a real short burst of ATP. Creatine phosphate works the same in all types of muscle, and that's sort of your first defense of getting ATP. We can take glucose or glucose from glycogen and put it into a process called glycolysis. You break the glucose in half and you get 4 ATP. You had to use ATP, so you net 2 actually. The pyruvic acid that you get from glycolysis, you can put in oxidative phosphorylation. The thing about oxidative phosphorylation is you can use all kinds of substrates, not only pyruvic acid, but amino acids and fatty acids. And then you get a big output of ATP with oxidative phosphorylation. So different fibers use different amounts of these processes. So here's a cross-section of some muscle, and we see some of the muscle fibers are really big, but they don't have very many blood vessels around them. And some of the muscle fibers are much smaller, and they have lots of blood vessels around them. Then we can use the same picture, or a similar picture, and look at it in terms of a staining technique, looking for oxidative proteins. And you see these smaller fibers are your slow red twitch oxidative fibers. They're the ones that get recruited first. They're the ones that don't fatigue very much. They're the ones that produce less tension. And they're the ones using oxidative phosphorylation. Then we have these big white fibers. These are your fast glycolytic. They're big around because they can produce a lot of tension. They contract very quickly, but they fatigue really fast. And these guys are using mostly glycolysis. So here's our slow oxidative fibers. They don't produce, they produce a small amount of tension, but they can just go on forever. Those are your postural muscles. They just can contract all day long. Now we have some intermediate fibers, fast oxidative. they produce a little more tension, but eventually they do fatigue. Then we have our fast glycolytic fibers. They produce the most tension. They're very fast, but they fatigue very quickly. And I have a nice table in your notes that shows, you think about, I'll go back here. You think about these guys. These are going to have lots of mitochondria. They're going to use lots of oxidative phosphorylation. They have lots of blood vessels. They're colored red because they have myoglobin and because they have all those red blood vessels around them. These white fibers are going to be bigger. They're faster, they're stronger. They actually have a myosin that hydrolyzes ATP much faster, and that's what makes them so fast. They're going to use lots of glycolytic enzymes, and they're going to use glucose as a substrate, so we'll think about that. So finally, how are you going to move your arm? Well, here you have a bicep and a tricep. So there's a place called the origin. That's the attachment that doesn't move. And then you have the attachment called the insertion. So when this bicep contracts, it moves the arm up and in flexion. Then we have an antagonistic muscle called the tricep. And when it contracts, its insertion is up here. Its origin is up here, and its insertion is down here on the ulna, and it pulls the arm so it extends. So we have pairs of muscle that are antagonistic pairs. Quite often your brain will activate both of those in a co-activation. What does that do? That stabilizes this joint. If you have a heavy load that you're lifting and letting down, you have both of these muscles engaged, so you can control the load and stabilize that joint. Also, it turns out that the muscles attached to these bones acts like a liver, acts like a lever, not a liver, acts like a lever system. And you remember from physics that you have a lever and a fulcrum and that sort of thing. And if you want to lift a really heavy load, you can move your fulcrum really close to the load and you can be really, really powerful. What's the problem? Is that you lose how high you can lift the load. It's the same kind of thing. So humans are basically balancing power versus range of motion. There are some primates that aren't as strong as we are, but they have more range of motion. There are other primates, something like a gorilla, that are way stronger than we are, but they don't have the range of motion we do. So the skeletal muscle system and the bones work together as a lever system to balance power and range of motion.